correlative to the underlying process. But as a result of our discussion previously, we have a relationship between what we're getting and what we would sort of like to have that is a bit between the ideal solution and sort of the best case scenario or optimal solution that we can look for in that particular case. So given the constraints, an optimal solution is the one that we have refined to the maximum degree, and an ideal solution is essentially the theoretical solution for the environment. In some cases, this book will kind of throw those two terms together. I don't mind it in a sense because we will never really get to the optimal answer. We're going to get to a realistic approximation, and that realistic approximation is going to be essentially our objective function. But one of the things I want you guys to keep track of here, and I want to talk about through this, is the idea of reducible versus irreducible error. The question lies, what portion of the error is due to simply the variance of the data model, and what portion of the error is due to our incapacity to fully and adequately balance the fact that this is a sort of ill-posed problem, right? Go back to the previous slide here and let's look at something for an example of the understanding of what is meant here. How many values can be proposed for the value of the expected value of y for x, right? There's one expected value. I've already told you guys about talking. Really? Is that important? I will throw people out of my class if you're going to get that disrespectful. There's other people in here who are looking to learn. I do my best to try to present the material. Please stop being distracted. As you can see in this particular case, there are multiple values that are technically valid solutions at each value of x, right? So the correspondence of a singular value of y, a singular value of x, a underlying functional approximation, is ill-posed, right? The reason why it's ill-posed is because from the data set, I can't simply select a single value to be the representative for the values of y as an output. Given that, we can look at this system as essentially if we were to attempt to minimize it from a matrix type solution, we would imagine that each value in that matrix would essentially operationally be a value assigned to a variable. So if we think about it in this sense, regression is a bit like trying to solve a system with more equations than variables, right? What happens whenever you have more total equations than variables, right? I have x, y, z, right? And I have 50 equations. How many solutions are there to that problem? There's an infinite number, right? None of them are going to be perfect, and none of them are going to resolve all of those equations, because if all 50 of those equations are technically independent, then each one of them is an expression of its own relationship between the items considered. So, as each data point represents its own understanding of value of y as x changes, we're also going to end up with that variance relative to every single point x being provided with, or providing us with, a reasonable localized approximation. So utilizing this sort of brute force approach of taking the average of the values that are sort of in that little column around which we're interested in is a bit like a probability density function, right? So if we were to flop this over on its side and look at it along the length, so we imagine the line going through here, and then we see just along x, right? Just along x of 4, we're going to have a series of point distributions along this space. Higher density is going to start to appear closer to this line. Why is that? Because it's closer to the expected value. So when we think about our underlying distributions, let's just say that at this given point, what is the likelihood of the next value to fall in this space? What does the probability function look like if I was to sample this one more time at x of 4? It looks like a Gaussian distribution centered orthogonal over top of that space, right? It is the distribution or the density function is respectful or reflective of that singular value. So the expected value, whenever I say E expected value, I'm talking about the mean of the distribution as it sets with respect to the singular value, x of 4. I have a visualization of that in one of my other supplemental slides, but we'll get to those a little bit later on. So for definitional purposes, while the expected value and our understanding of this regression function is related to this system of probability density, right? So you have a space, you have a certain number of values existing in that space, and then you have the likelihood of the next value to happen. What is the reason why we would say that we would use a likelihood assessment relative to this modeling function? Isn't the whole goal to estimate how close, as close as possible we can to what the next value would be if we collected another single sample, right? That is the very nature of the process we're looking for here is what happens if we continue sampling? What happens next to add to the system? Largely we understand through the central limit theorem and the idea of aggregate density with regard to ordinate systems, we will see values aggregating towards the mean, towards the expected value of that distribution. So the likelihood increases towards the mean. So we essentially calculate the mean at each individual point, then we say that the line that we placed there is going to likely be closer than other values. Now, part of what's happening here is something that we haven't really shown a lot, but the idea of a regression function works essentially or significantly with a distributional space such that we have a line that attempts to sort of bisect the relative cloud of points available. Now, how do I determine whether or not this is a good line for this group of points, rather than, let's say, some other line, this line? How do I determine which of these is better?
The straight line, that's not the dotted line. It's better because it's close to most of them.
Okay. So what we're looking at here is a series of vectors, essentially, can be drawn from each individual point to their sort of relative normal on the line itself. And what we're actually getting here is an aggregate, or the aggregate sum, of all of those vectors' magnitudes, right? So that is the magnitude, the total magnitude of error. We say the total magnitude of error squared, that was what we were doing earlier, relative to each individual line. The line that has the lowest or the least or minimum squared error, right? Total magnitude of distance away from the points, right? It is essentially the line that satisfies the largest number of points with the minimum amount of error vector as a result of those incidents. So if we were to look at it along this axis, right, the summation of error values is going to be all these different individual vectors adding together to put that point in the center. But the real error vector we're interested in is, let's imagine that we have some new point here, right? And we're looking how far away that new point is from the line in the projection space. That's how we're going to assess it. We're going to minimize it relative to one set of data, and then we're going to assess it relative to a set of data we haven't seen. Now, this is the portion that we'll talk about in a little bit, but the construction of this process is summational. So when I say reducible error, in that particular case, in a simple two-dimensional line, the reducible aspects of the error are going to be adjusting the coefficients for the underlying function. This case being a linear function, just slope-intercept. All right, so the slope and intercept are adjustable, but there still remains a degree of error that I will never be able to adjust for. This is a factor that really does matter, because we have a tendency as developers and engineers to think about things in terms of gonna be able to get it to zero error, right? It's gotta be able to minimize, it's gotta get low. Well, there's a theoretical maximum to how much you can reduce this. The spread, the total variance, the space over which those points are separated from one another, obligates us to create a line, if I want to just stick with a strict linear regression, obligates us to create a line that is the best one we can come up with relative to that total amount of error. So, when I say something is reducible, this means factorized relative to the scale of my guess, right, subtracted from what the answer should actually be. Once again, supervised, because I have the answer, and then I have my guess, right? So I have y, which is the answer, and then I have my guess that I put together. And I say, how far away was my guess from what the answer should have been? That is my mechanism assessment, yeah.
So is the irreducible error, is it about addressing overfitting, or is that?
The overfitting is involved there. You're stepping one little step ahead of time. All right, we have some slides on that, so I don't really want to like go too far into that space. But what if I was to say, let me just make this rough approximation. What if I were to say that I could create a line or have a poly fit like this, such that the poly went through all of the points on this system, right? It goes to every single point, okay? You could create a polynomial where, relative to that polynomial, each of those points now sits on that polyline. Do you think that's going to be a good indicator for future potential, right? How good is the likelihood that a new value is going to fall on that line? That's another consideration. You can increase something, we're talking about this, increase the flexibility to attempt to minimize this, but what ends up happening is this doesn't go away. The irreducible error is still irreducible. The model that you've created that's supposedly a zero error model is only going to be a zero error model for the samples you have, not any new samples. So what's the quality of a model that perfectly fits the data you have and is complete garbage for any new data? Zero. There's zero utility for a model that has perfect fit to what the previously collected, the a priori, and has no utility for the post-assessment, a posteriori, right? Without any future projection capacity, without robustness, without generalizability. That's one of the terms we use to describe this is generalizability, okay? So let's talk about how we typically estimate F. In this particular case, we're going to use something called neighborhood approximation. Now, neighborhood approximation is a relatively good way to go about this process, but it is somewhat computationally expensive. However, it is more difficult, or I guess you could say it is more costly to execute than running a traditional slope-intercept form model, right? So neighborhood approximation will essentially say that for some given value x, let's just keep the value 4 in this case, we're going to create an expected value of y relative to x, meaning we're going to take the spatial localized average for a window, right? Not only just the values that occur exactly in the space of 4. Notice, there are no specific unique values that actually occur at x of 4 in this particular space. Yes?
How big is that window?
That's a question that is model specific. That's a good question. I like that question. What do we think is going to happen as we increase the width of this window?
The error will be there? More error will be there?
In some cases, yes. But it's the type of error. What are we looking for in terms of type of error?
Well, I was gonna say this, like, if you like widen the range of that certain point, then it would less represent the actual value there.
Okay, that's correct. So the aggregator, overall, the reason why the error is in place is a result of the fact that it's essentially muddying the water. Okay, we want specificity, but at the same time, we want generalizability. We're going to talk about this. This is a trade-off. This is a trade-off. This is something that's related to a concept that we're going to discuss today. It's going to be called the bias variance dilemma. All right. So how much space you want to try to allocate to this window? You want to increase the number of samples, but whenever you do so, what do you end up doing? You make the individual data points less valued because they're being aggregated out, they're being averaged. So you sum all those values together, divide by the spatial characteristics, you get a smoother curve, right? But that smoother curve is less defined. So typically the things that we do that involve widening the search window, increasing the range of the input value space, often create systems that are more, they change less per unit, right? Because they have a wider window. They're averaging over a wider space. This tool is, this process is used often with sensing technology, right? Many sensors use windowed approximations to determine their output values. As a result of the variance that you might see for something like an ultrasonic or magnetic sensor, or even light sensors, we often will take many samples over a duration, right? And we'll average them all together in order to attempt to minimize the variance that's resulting from the uncertainty, or the range of uncertainty of the sensor value capacity. So within that sense, we're oversampling and then we're aggregating. That creates a smoother approximation that does attempt to average away some of the error. But as a result of the average away of the error, we end up with less specificity, right? Lower resolution. Take a picture, right? And you guys have always seen what a blurry picture is, right? Why are pictures blurry? Because from one pixel to the next, there's less distinction. They're more similar to one another than they are different. Sharp edges, high definition for set points, operational set points in a system, are defined by sharp changes, high frequency elemental changes in that particular space. So we're eliminating high frequency elements, and we're actually going to create a smoother operational output by using a wider neighborhood approximation. Now we will say that our underlying system is the approximator function, or f hat, right, that's our guess function, is equal to the average of the expected value of y for x, which is a set of elements n, where this n here indicates a neighborhood of values, not a specific range or not a specific value of x, but a window thereof. Now, this says that the neighborhood can be pretty good for a small value of p. What do I mean by p in this particular space? P is going to be something related to the dimensionality, right? So how many dimensions the system works in. So this says that low p's, or values of p less than 4, and relatively large n, which is the neighborhood size, right, or the number of samples within the space. So in systems with relatively low dimensionality and taking pretty wide sampling spaces, taking wide-ish areas of window, we'll get something that is usable. All right? They're not great, but they're not terrible either. So that's why we talk about the idea of smoothing functions. And we'll talk about splines and kernels later on. The idea here is something that's called nearest neighbor method overall, right? So we're talking about neighborhood process, but nearest neighbor methods are those that can work in larger systematic spaces. They are what's called lossy when P is large. The reason behind this is that curse of dimensionality. Okay? Let me grab something real quick here. That curse of dimensionality is related to our understanding of a spatial distribution and relative density. Just give me 1 second.
Spatial distribution and what?
What? Absolutely. Every time you log into this thing now, you guys have the same problem where you have to use your app every time you log in? It's an absolute pain. Oh, and then sometimes it doesn't work. Oh, there it is. Okay, sorry, I'm trying to get a slide here, and I'm having difficulty getting to my canvas for a second, so it's being a pain, but I'll get there. When we think about the curse of dimensionality, we are interested primarily in how much space is being allocated to the total search area, right? Whenever I say high dimensional spaces, what am I talking about? Anybody give me an idea?
Can you repeat that?
High dimensional spaces.
Okay.
So a dimension is an axis that you can deal on,
Okay.
and it looks like having more than 4 is how they're defined.
Now, in this particular case, the reason why I'm saying having more than 4 is high is that the volume of that space changes. All right, I'm trying to show you my PowerPoint slides because these, I think they do a better job than I can explaining it verbally. But, all right. Why is it on that screen? I don't get it. I don't get it anymore. It doesn't make any sense to me. The curse of dimensionality, overall. A single dimensional space is what? The number 1, right?
Yeah.
A 2-dimensional space is a flat planar surface, and then a 3-dimensional space is the aggregate of cube space as a result of multiple planes stacked within one another. Yep. You have a question?
No.
Okay. So, as a result of the number of spatial characteristics, so the increase in spatial volume, in order to adequately define that space, i.e. the interactions between the elements in the space, we're going to take into consideration additional samples to be able to make up the edges or the standard characteristics of that specific space. The example given here is, let's start off with a number of elements for a neighborhood space, and we'll just start off with a localized neighborhood of k equaling 1 for the nearest neighbor, meaning that we're only going to use our most localized immediate neighbor as an understanding of determining which class grouping I'm in. So if I want to try to determine whether I'm in group green or group red, all I'm going to be able to look at is 1 to my right or 1 to my left relative to the K association, right? That's the region association. So if I wanted to do this from a classification standpoint, how much sampling density did I have there? It's full density, right? Every value that can be filled in that space is filled. There is an example of a specific individual for each unit of space allocated to this dimension. So this is a 1-to-1. What happens whenever we go into 2-dimensional space? Now we're going to keep the same number of samples, and we're going to distribute that number of samples over 2 dimensions. What has happened?
It's It's spread.
It's spread out, okay? The relative sort of entropy is taken over and spread everything physically out over the space. Now, the local regionalization, right? If I'm green here and I can only look at one around me, I'm gonna have a hard time creating some kind of interassociation as a result of that, right? So the higher the dimension goes, the wider I have to get in terms of my association index in order to be able to make some kind of meaningful assessment. So all of our models are based upon sort of spanning across things, right? You want to take a point, you want to take another point, and then you want to determine what the values might be in between. Guess what? You put a line in there, and you say, hey, I can now interpolate all the potential values in between it. If you put those things way too far apart from one another, what degree of certainty that do you have that some other point might not come in and take place in between the 2 points you selected? Something might change. So your confidence, the ability to adequately model the underlying system, relationship between space, right? How we determine what each individual here is in this space. We have value at x1, x2, right? There are two features, and then we have a class, or what type of individual is being acknowledged in that space. In order to be able to associate that space fully, I now must have a sample density of the 9 squared, right? So a square sample density relative to the spatial dimensionalization, in order to be able to have the same density as it was recognized in the one-dimensional space. How much more difficult is this to collect than normal, right? To collect one sample relative to each spatial characterization. This may actually be functionally impossible. So in order to be able to meet the same density, i.e. have the same confidence in one dimension, in 2 dimensions, guess what? We have to have a theoretically impossible number of samples. What happens in 3D? This is the part where we say, why past 4 it's a problem? Why 3 or less is a relatively decent issue for neighborhood approximation. At 3 dimensions, this system starts to get gigantic, right? The cubic is taken into consideration. It takes 729 samples to fill this space, all right? So this, I don't have a filled version of this. I do have a filled version of this, but it's not visible. So in order to be able to reach this 3-dimensional spatial density, we have to have 729 samples relative to the original 9 samples we had on the first 1-dimensional space. So when I say cursor dimensionality, what I'm talking about is that the ability to distinguish useful representative spatial characteristics of the individual samples, it becomes more and more problematic to be able to find an ideal surface or line or polyline, whatever you want to use for your function to regress this, that will adequately describe the relationship between the individual points in the space. What we often see in distributional space, this is a data set called SAFAR 10. This is a relatively high value set, right? So there's 60,000 values over 10 different classes of images, and these are 32 by 32 image data, and we've reprojected them onto 3 axes, U, Y, and V, and this is the color data representations of some of the content, some of the image space. Notice, how high density is this truly for the entire 3-dimensional space? Not much. There's a lot of it toward the center of the spatial aggregate, but the density falls off quickly towards the edges. This seems that it makes sense according to what we normally would understand about data and data density, that the more space that we have to cover, the more samples we have to fully and adequately express that space or the events happening within that space. That is what we're referring to when we talk specifically about the cursor dimensionality, all right? So, when we have a reasonable factor of n values, we try to bring the average systematic variance down to a reasonable number, let's say something below 10%. A 10% neighborhood in high dimensions will no longer be able to be local, right? So the larger the space relative to the dimensional output, in order to reach the same degree of variance control by using a neighborhood approximation. Variance control would be what? Controlling noise, controlling the instability of the variance factor. So if I want to smash the variance down, I do so by averaging the values out in a space. So in order to bring that averaging down below 10%, I would have to have a giant sphere of points in order to be able to eliminate that down to a singular point. What ends up happening after a certain degree of expansion of your sphere of interest is that you end up with just the average of the entire data set. Okay? It ultimately ends up flattening out to a singular point that isn't any good at providing you with any likelihood assessments for the output. So as we see the neighborhood system approximation increase in scale, the larger the scale values, we see that as P approximation, this is the dimensional approximation, increases, this is a characteristic of the necessary radius to meet a specific fraction of that volume expressed within that space. So by the time you get up into 10th dimensional space, in order to meet a fractional volume of your 10%, right, a localized regional variance reduction, you have to have, what is it, like almost 50 times the magnitude of radii in order to be able to meet this space, right? So this starts out right around 0 for the minimum spatial dimension, and this takes in a very large area, an area of 1.5, in order to meet that minimum amount, minimum density of the 10% neighborhood. Okay, everybody get what we're talking about there? That one's not, it's not a super complex idea, but it is one that's going to stick with us for a while, and it's one that's going to keep hindering us right along, is that the cursive dimensionality will create problems for us to find ideal models because they may not have enough information to make their decisions with. They may not be descriptive enough. So there's a trade-off between the flexibility of the model, how much it can change and adapt to the data, and the number of dimensions that it can operate in, as well as the acceptable degree of error that we're going to be able to put up with in our propagation or our approximation. So all those things have to be balanced together in order to make this work. Linear models are systematic parametric models. We've seen these beforehand. And essentially what's happening here is that FL, some linear model, this is the ideal linear, is going to be comprised of beta naught, which is our intercept, beta 1, x1, right? What's the x sub? What's the x sub? This is the first feature of the feature vector x. Okay, the feature vector contains multiple features, and we say this is the first of the multiple features that is kept. So in this particular case, we have p-dimensional space. So this is the universal model, and this is the ideal model, right? The one we're not going to use. This is the theoretical version. But we would say that each of these parametrics are going to be provided by a beta. This beta is a scaling coefficient. It is simply a number which we're either adding or multiplying by. So we're multiplying by it whenever we're creating the scale of the degree of value or the weight that we're assigning to that feature. So each feature will have a certain degree of value relative to its capacity to help us predict the future. When we assign that particular value, we're saying we're giving it a weight, we're giving it an emphasis, a significance. The beta naught coefficient is simply added on as a metric to be able to adjust for averages or the means of global data characteristics. Linear models are almost never correct, all right? So even if we had this whole system of p dimensions, right, plus 1, that's our beta naught, right? So we have p betas, p coefficients, plus 1, plus our intercept, right? That's often called the bias term. Don't confuse the bias term with the notion of data biasing. That is a complex concept because bias follows a lot of forms. Many people conflate the idea of using the term bias with the socio-political and socioeconomic considerations of the world in general, right? Models shouldn't be biased. Guess what? All models have to be biased. Bias is simply what happened before that informs me for the capacity for future predictive characteristics. Without an intercept to the slope, that line could literally fit anywhere on the axis. The bias anchors me. It provides me with a frame of reference relative to the mean of the data set that I'm interested in. And that in and of itself is a centralizing factor. All right? But that's where we'll talk about in a bit, the idea of bias and variance characteristics is a little bit different than this bias term. This bias term is simply beta naught. It is the one that tells us where to start from. It is also called the intercept of the slope intercept. Now, while I say that this is almost never correct, it is not that it doesn't do a good enough job. It's just that it really, many things in the universe, linear. Are most things in the universe linear?
No.
No. Most things at least follow some form of curvature or parabolic, okay? So when I say the reason why this is almost never correct is that it's an oversimplification of the underlying system. Okay, what ends up happening here is this is just a relatively simple example of our banana data again, right? We have our banana. Our banana data, it says, I put a line through the middle of the banana. It's close, it's not awful, but it's not as good as it could be, okay? So I add a degree of freedom, right? I add a little bit of flexibility to this line, and I allow it to warp a little bit, right? To be able to conform to the underlying data, and I get something that's a lot closer to the underlying system. What are the risks involved with doing this? What do we think? Put too many degrees of freedom, put too much flexibility, give it too much freedom, it'll start to cheat, okay? Just like any good student, right? We're trying to teach these. It's machine learning. We're machine teachers, all right? So whenever you're teaching the machine and you give it too much freedom, all right, it's just going to go to ChatGPT and get all the answers. Okay, that's really what's going to happen. I'm over-generalizing, but the idea here is it has the data. It can see the data. What's it going to do whenever it has too much flexibility? It's going to stop making general rules and start making specific rules. It's going to create little cheat sheets to tell it what the answer is to each individual point, rather than learning the rules that govern how to determine the total of the system. So this is a characteristic here where first, we're acknowledging linear models are capable of describing many systems, but not describing them perfectly. This is an idea of how we might take a surface, right? And remember, what's a line in 3 dimensions? Surface, okay? It's just simply expanding our understanding. So this is a nice flexible surface. This is our little smooth, adjustable plastic surface. It does a relatively good job at creating a correspondence between the items we're interested in here, right? So we want to say, I want to fill in, if I want to put in some level of education and some level of seniority, let's say right around here, I don't have any specific examples that tell me what the pay rate would be at that space. But I have other elements around me that can inform what the surface should look like relative to that higher dimensional space. So if I make a smooth surface like this, what's one of the problems with it in terms of attempting to understand what's going on with this system? Anybody want to tell what, just think in your head what the equation for that might be like. It's nasty, right?
Yes.
How things change, where it changes relative to the space, where you're going up and down. It's really hard to interface in your head how that works, okay? So while a linear, a flat surface, what's this look like equationally, right? It's simple. It's just 2 slopes, each one giving you an indication of the relative declination of the surface. We talk about this in a concept, and we'll mention it again later on, but we talk about this relative to something we call explainability, right? The utility of the model is dependent a lot on how much you can use it to generate new actions in the future. If you don't understand how the items are working with one another in order to create the output, then you can't really get in there and change those individual elements. You can simply react to them by creating a model of that system at fine granular detail. So there's a balance between explainability and accuracy. Explainability is like the idea of saying a parabolic surface versus a simple slope surface. A slope is far easier for us to visualize, right? Unless you get in there and start graphing it, many times a high dimensionality per parabolic surface is just too complex for our minds to integrate. But rise over run, a change in value as you see a change in value over distance is easy for us to understand. We say, oh, hey, we have a direct relationship between those items. The reason why linearity is preferable and the reason why in many cases is that linearity has this characteristic of being very explainable. What ends up happening if we allow the surface too much flexibility, right? We give it a little bit more, now we give too much, right? Why do I say we gave too much? How much error is present there? None, all right? We had a little bit here, we have none here. Every single point on this line has an exact correspondence to the planar surface. When I say that there should be probably a little bit of error in your system, that's just a result of an incongruency, right? Variance in the underlying data. That's what I mean whenever I talk about the idea of overfitting. This model has overfit. We have given it too much capacity, and it has changed to adapt overly towards trying to minimize all error in the system. Now, what happens when a new point is placed upon that surface? What is the likelihood that if I kept all these points, but then I add one more, I sample one more point, what's going to happen now to the error of the surface if I don't change anything? That point is going to have error, right? The reason why is because I don't have that point to adapt to in the training process. So next time, on Wednesday, we're going to talk about the idea of training and testing, right? A training environment is where the data we start with. It's the data we make our initial understanding with. And then testing is when we have some new data that we set aside that we're going to check and see whether or not our initial guess was a good one, right? I give you homework, and then I give you the key to the homework. You can check to see if you got it right. But then when I give you a test, right, you don't have a key to check against. So a test set is whenever we are evaluating whether or not the model learned from its mistakes in the past, and whether it's learning to generalize or whether it's memorizing specific examples, right? So this is a balance between generalization and memorization and the ability to assess whether a model is approaching its desired targets with regard to performance. All right, so from here on off, we're going to talk about trade-offs and prediction accuracy, good fit versus overfit, and parsimony, the idea of explainability with regard to black boxing. Any questions?
The last slide, what black boxing?
Oh, we'll talk about it. I'll bring it up. This is just a look ahead at where the first slide we're going to look at.
Okay.
Parsimony is models. Parse means to cut up, right? Parsimony is the ability to decompose it into explainable elements.
Okay.
Black box models are modeled for one giant jump. We don't know what happens inside. Parsimony is modeled when we can see all the individual gears and how they're working together. Thank you. Absolutely. Take care. Yeah, I posted these other slides as well. So I made It says, I want to look at the y-axis, the x, this is the expectation. These are the individual values. So if I say what is the expected of the average of the error. Remember we're talking about the average of error each That is one of the error equations called mean square MSE. It is, we use this one. So this is the functional equation, we use this one as part of minimize. We'll use it whenever I'll show you another version of it. That's the one we use, okay? It's very similar to that. We don't put expected value, we actually say MSE, or mean of, that is, what is the mean? That is the aggregate value over number of samples. So we need a value in there that's not in that equation. That equation is incomplete, it's conceptual, it's incomplete. So what do we have to do? We say aggregate sum of all error over the number of samples in the given space would give us the mean of the sum of square errors, right? So it's sigma y minus f hat quantity square over n is the actual equation. Get what I'm saying? Okay, cool. I'm just trying to give you like all the equations. I'm giving you that. I'm trying. We're sort of conceptually or structurally deriving as we go forward.
So this is an actual equation, and this is like the error equation, right?
It's part of the error equation. Correct. Correct. Yeah.
So
And this is simply the conceptual one, right? So that is
a
an F.
conceptual one.
Yes. Yes. F.
So this is it's not equal to this, right? It's not.
It's not fully equal. No. No, it's not fully equal.
So this is error equation. This is the conceptual equations
Mhm.
for understanding the equation.
So think in here, right? So we still have x equal x, right? So
Yes.
this is for all x.
For all.
So e of y, right, for f of x. If I minimize the function, so it says minimize this value function, will minimize
You
the
are
error of that
minimizing
function.
this.
Correct.
Oh, I get it.
Okay. Cool.
So
Good.
sometimes it's difficult for me to understand.
Some of these things aren't written like super perfect, but honestly, they're good enough. And where I look at it and I say, some people get it right off the bat, other people might struggle a little bit with seeing what's happened there. Make sure to read the text along the lines in order to be able to see what they're saying.
Yeah.
A lot of times they should use like more standardized notation,
Yeah.
like, you know, the prescriptive notation, like dots and linear prescriptions. But later on, they do a little bit better